Hello, everyone, and welcome to the 48th Surface Ventures keynote webinar. Please say hi in the chat and tell us where you're joining from. See that Michael, hopefully, has already said hi from Belgium. Great to see you. Yeah, it's always good for us to see where everyone is joining from. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. Today, it is my pleasure to introduce Dr. Pranjal Notial from Oklahoma State University. Pranjal is an assistant professor of mechanical and aerospace engineering at Oklahoma State University. His research focuses on advanced materials processing and experimental mechanics. His group's current research focuses on tribology, nanostructured materials, and cold spray additive manufacturing. He received an early career research award from the Society of Tribologists and Lubrication Engineers in 2023 and was named a senior member of the National Academy of Inventors. Many thanks to today's partner, PCS Instruments. Alexander McLaren will be joining us later in the event to deliver a presentation from PCS Instruments. We'll also be releasing poll questions and later handouts from them throughout the event, and I will indicate when those are being released in the chat. As we go along, please type your questions for either Pranjal or for Alexander, into the chat, and they'll be marked for the Q&A session at the end of the event. We're planning to go for around 60 minutes in total today. We will be sharing a link for your attendance certificates later in the event, so I will specifically indicate when that is available. And it would be great for you to please post about these and tag us on LinkedIn after the event. So without further ado, let's welcome Pranjal to the stage and proceed with the webinar. Good. Welcome, Pranjal. Great to have you with us.
Hi, Sam. I hope you can hear me.
Yes, coming through loud and clear.
All right. And is my video visible?
Yes, we can see you. Okay, and it looks like the screen share is starting, which is great. There we go.
Somehow I don't see my video working, but if you can see me, that's great.
Okay. I can see you just fine. There we go, and I can see the slides. So all good. Please take it away.
Thank you, Sam. Thank you. I appreciate this invitation to give this keynote today. And hello, everyone joining from all over the world. Nice to interact with you today. So mechanochemistry is a topic that deals with the study of chemical reactions under mechanical stresses. While this is broadly applied in chemical and material synthesis, the topic of mechanochemistry is particularly important in surface science and tribology, where two surfaces come in contact, and there can be significant stresses generated at these interfaces. We can design mechanical systems in a way that we exploit these elevated interfacial stresses to mitigate friction and wear and improve the efficiency and longevity of mechanical systems. So I'm going to show you in my presentation today two particular examples of how we can exploit mechanochemistry in tribology. And one of them will be on catalysis. The other one will be on electric field-induced mechanochemistry. Before I get started with my talk, I would like to mention key contributors to this presentation. So the results I will share today were collected by my PhD students, Bunty Tomer and Foyez Ahmad. And this work was conducted in close collaboration with Professor Ritesh Sachan, Professor Dave McElroy's research groups at Oklahoma State, and with Dr. Jun Q's group at Oak Ridge National Lab. So traditionally, when we look at chemical reactions, we start with reactants, which are in a state of local equilibrium, and we provide energy, which is typically heat. This helps reactants cross an energy barrier to form a product. Now, when mechanical stresses are introduced into the reaction system, that reduces the effective energy barrier required for the chemical reaction to proceed. As a result, the reactions can take place faster, and they can take place at lower temperatures than in traditional thermochemistry. And this is captured here by this Arrhenius style equation, where the rate constant K scales exponentially with the applied mechanical energy, EM, in this equation. So as you can see, there is a thermal activation energy. The mechanical energy reduces this energy barrier, which helps the kinetics of chemical reactions. The mechanical energy can be in the form of compression, shear, tension, etc., and that depends on the molecules you're dealing with. The concept of mechanochemistry is extremely important in tribology and lubrication, particularly. And I will show you one example here of zinc dialkyl diethiophosphate, which is a very popular engine oil additive. This additive reacts at sliding interfaces because of mechanical stresses and heat to generate tribofilms, right? These are surface-bound films which consist of phosphorus, sulfur, zinc, iron. So essentially glassy phosphate films. And once these films form on the surfaces, they protect the underlying metal from wear because of elevated contact stresses. In the past, research group of Professor Robert Karpik at the University of Pennsylvania showed that the growth behavior of these tribofilms is strongly dependent on contact pressure and temperature. So as the contact stresses are increased, the growth rate of tribofilm increases exponentially. Similarly, temperature also provides that exponential boost to tribofilm formation. So these results are consistent with the stress-assisted reaction rate theory I showed you earlier on the left-hand side of this presentation. So I hope this background provides you context on the importance of mechanochemistry in designing lubricants and preventing friction and wear at sliding contacts. In my talk today, I would like to present two important types of mechanochemical reactions. First, I would like to discuss catalytically induced reactions and share our group's latest discoveries on multi-principal component alloys as catalysts for mechanochemistry. Then I will move on and talk about the study of mechanochemical reactions under electric fields, which is becoming a very important topic because of electric vehicles, because the mechanical systems there can experience both mechanical stresses and electric fields simultaneously, affecting the behavior of lubricants. So catalysts are widely used in thermochemistry because they can assist chemical reactions and accelerate the formation of products. They do that by reducing the effective energy barrier for chemical reactions and providing surface sites for the reactants to attach and react. The concept of catalysis was extended to design lubricated systems or tribological systems by Professor Ali Erdemir and co-workers in 2016, where they designed catalytic nanocomposites that consist of transition metal nanocrystals like copper and transition metal nitrides like molybdenite in this case. So as you can see, they applied a coating of these nanocomposites on a steel substrate, and then they conducted wear tests of these coated surfaces. They observed that these coatings resulted in negligible wear of specimens, as opposed to steel surfaces, which under identical conditions experience tremendous amount of wear. When they closely inspected the surfaces of these tribological components, they observed that the surfaces were covered by a carbon-based tribofilm, and Raman spectra of these films shows characteristic DNG bands that are often seen for diamond-like carbon coatings. Now, diamond-like carbon or DLC coatings are known for their excellent anti-wear and low frictional properties, and they are engineered by processes like physical and chemical vapor deposition. But in this study, they showed that by using a catalyst on a sliding surface, the formation of DLC can be induced in situ during the tribology experiment. I should mention that they did this experiment in the presence of a hydrocarbon, so that there is an oil, a polyalpha olefin oil molecules at the interface, and the formation of these carbon-based tribofilms are induced by catalytic conversion of the PAO, the oil molecules, in these experiments. There have been multiple other reports on these catalytic nanocomposites, and different compositions have been tested, and I'm showing you some key references here on this slide. Apart from this, there has been some work on nanocrystalline platinum gold alloys from Sandia National Lab. So these alloys are nanocrystalline alloys. They consist of platinum and gold, where the gold atoms segregate at grain boundaries and make these nanocrystalline alloys highly stable, prevent grain growth. So the researchers at Sandia, John Curry and co-workers, did wear testing of these nanocrystalline alloys. And here I'm showing you the specific wear rate on the y-axis versus friction coefficient on the x-axis. And they observed that the wear resistance of these platinum gold alloys was extremely impressive, surpassing the performance of most engineering alloys, and actually matching up to diamond-like carbon coatings, which are known for their excellent anti-wear properties. Later studies by this group showed that these platinum gold alloys were also inducing a carbon-based tribofilm formation. So here I'm showing you the platinum gold alloy. The tribology test was conducted, and at the end of the test, they observed the formation of a nanocomposite film, which was composed of carbon combined with some wear debris. And there have been a lot of studies on this system in recent years from Sandia, as well as Professor Filippo Mangolini's group at UT Austin. And they have discovered the structure of these films and the nature of these reactions can be controlled by changing the composition of platinum gold alloys, as well as the conditions play an important role in the final composition. I should mention that these experiments did not rely on oil molecules to form tribofilms, but actually these were conducted most of the times in nitrogen environment. So inert gas or nitrogen gas, and the nitrogen gas contained some organic vapors. So it is those organic vapors that reacted on these catalytic surfaces to form carbon-based tribofilm. Recently, researchers at Northwestern University extended this concept to design catalytic steels. So they designed steel alloys with higher concentrations of known catalytic metals like chromium, molybdenum, vanadium, copper, nickel, and pardon the abbreviations. There are all these abbreviations here, but essentially some of these compositions here labeled as A2, D2, M2, CF2, they contain higher concentrations of some of the transition metals that are known for their catalytic properties. And as you can see on this plot, the wear volume is negligible for some of these compositions, as opposed to the 52-100 steel, which is the bearing steel, and which does not contain very high concentrations of these catalytic metals. So clearly, these catalytic elements, they improve the wear resistance of the steel. And later on, some Raman spectroscopy of the surfaces revealed the formation of a carbon-based film. And the greater the intensity associated with these carbon-based films, the better the wear resistance, as you can see for D2, which is a sample with very, relatively higher concentrations of chromium. So, so we can see from these prior studies that the incorporation of catalytic elements could provide an excellent pathway for inducing in situ formation of carbon-based tribofilms at sliding contacts, which then provide excellent wear resistance. So we are interested in extended this concept to design multi-principal component alloys as potential mechanocatalysts. And this is because, unlike traditional alloys where there is one principal element and then the solute atoms are added in much smaller concentrations, in multi-principal component alloys or high entropy alloys, we can have high concentrations or relatively equal concentrations of more than one elements. So this gives us the opportunity to play with multiple combinations of catalytic elements like nickel, chromium, molybdenum, vanadium, the elements which are known for their catalytic activity and which other groups have shown to be beneficial for inducing mechanocatalysis. We could potentially exploit their properties to design these catalytically active alloys and achieve excellent wear resistance at sliding interfaces. So that's what motivates us to pursue high entropy alloys to design catalytic surfaces. So we developed nickel, cobalt, chrome alloys. So we started with a medium entropy system. This work was done in collaboration with my colleague, Professor Ritesh Sachan's group at Oklahoma State. Their group specializes in pulse laser deposition of high entropy materials. So they deposited nickel, cobalt, chrome thin films with a thickness of about 100 nanometers for our tribology studies. And then they confirmed the structure of these films. And as we can see here, there is an equal uniform distribution of nickel, cobalt, and chromium throughout the film. Okay, so that's the sample we used for this study. And then to study the catalytic properties of nickel, cobalt, chrome, we used in-situ atomic force microscopy approach. So in this method, we use a sharp diamond tip, and we use that tip and we scan over the nickel, cobalt, chrome alloy. We apply very high contact stresses. We raster over the alloy over a predetermined area. And then because of the stresses, we hypothesized that nickel, cobalt, chrome will catalyze the formation of a tribofilm. So as the experiment proceeds, we stop intermittently. We take larger area scans so we can actually visualize the growth of tribofilm and quantify the thickness of tribofilm as a function of scanning time. So that's the protocol. This is the same method that was developed at UPenn in Rob Karpik's lab when they showed the growth of 0DP tribofilm for the first time. So using this method, we conducted some tests on nickel, cobalt, chrome alloy at a very high 12.5 gigapascal mean Hertzian contact pressure. And as you can see in this in-situ video, as the sample was subjected to contact cycles in the central 1 by 1 micrometer square patch, we saw the formation of a thin film. I should mention that we are doing this experiment in air. So essentially, we are relying on ambient hydrocarbons to induce these mechanochemical tribofilm formation. And clearly, nickel, cobalt, chrome is catalyzing the formation of these films. These stresses are pretty high. They're very high. These stresses usually induce significant wear and deformation of alloys. But in this case, because of this mechanochemical film formation, the wear of the alloy is mitigated. Because AFM provides great sub-nanometer depth resolution, we can quantify the formation of this film with good precision. So here I'm showing you the thickness evolution of tribofilm as a function of contact cycles. So within 100 cycles, we clearly saw the growth of the film. And as we continued sliding cycles, the thickness of the film increased. Thereafter, there was this slight removal of tribofilm, so from 300 to 400 cycles. And then after that, the film thickness reached a steady state or saturation, and there was no further change in tribofilm thickness. So we think this behavior is because in the beginning, the catalytic sites are available. So the hydrocarbons from the air come and absorb on the surface, and they undergo mechanochemical reaction because of the sliding AFM tip. Once those catalytic sites are exhausted, the growth of tribofilm stops and we reach a steady state or saturated state. Based on these measurements, we can then calculate the yield of the tribofilm, which here we call it the normalized yield of tribofilm, which is the overall volume of tribofilm generated by the end of the experiment, divided by the area over which the tribofilm was generated, divided by the time it took to generate the amount of tribofilm. So essentially, once saturation was reached, we were able to calculate the normalized yield of the film. We studied the yield of film as a function of stress and temperature. So we observed that the yield of tribofilm increased exponentially as we increased the applied contact pressure up to a certain point, that was about 12.5 gigapascal. Further increase in stresses did not promote film formation, but rather we saw some wear or removal of tribofilm because of severely high stresses. So these results show that the growth of tribofilm is promoted by stresses up to a critical point. We also studied the effect of temperature on tribofilm formation. And within a narrow window of 20 to 30 degrees Celsius, the temperature also promoted tribofilm growth. And we can clearly see an exponential increase in the yield of tribofilm as a function of temperature. When we increased temperatures beyond 30 degrees Celsius, we failed to observe this increase. And in fact, there was less tribofilm generated. And this can very well be understood by considering the desorption of hydrocarbon molecules at high temperatures. Because as we increase the temperature of the alloy, the hydrocarbons will tend to desorb and leave the surface. So that will undermine mechanochemical reactions, which is why we see this, a very narrow temperature window for growing tribofilms on this alloy. So going back to the potential energy surface I showed at the beginning of my talk, as I said, that there is an energy barrier that needs to be overcome for any chemical reaction to take place, and mechanical stresses lower this energy barrier. And this can be expressed by this Arrhenius style equation, and this is a more complex version of the equation I showed you before. So essentially, there is an activation energy that is needed for the chemical reaction to take place. When mechanical stresses, and here it's represented by sigma, are applied, that is going to reduce the effective energy barrier. And the effect of stresses is captured by this another activation constant known as activation volume. So the product of stress and activation volume provides us the overall mechanical energy that is done on the reactants or the system in the experiment, and that reduces the energy barrier. So that's the framework that is widely used for modeling mechanochemical reactions, including in tribology. So clearly, we can see that in our experiments, the contacts, there is an exponential relationship between the reaction yield and contact stress. So we can plot the yield versus stress on a semi-log plot, and we can get activation volume by performing a linear fit. So the activation volume was calculated to be 0.62 angstrom cube. Similarly, we can plot log K versus 1 over temperature, and that gives us delta U activation if you look at this equation. So that is 0.98 electron volts. When we look at the literature, the activation volume that we calculated is consistent with single atomic bond breaking and formation processes. So clearly, this suggests that the breaking or formation of bonds is the rate determining step for the tribofilm formation in our experiment. Also, when we compare with literature, the activation energy we observed is comparable with other catalytic reactions that suggest that the dehydrogenation or the breaking of carbon-hydrogen bond is an important rate determining step for converting hydrocarbons to carbon-based tribofilms. So based on these calculations and experiments, we think that in our reactions, the hydrocarbons from the air get absorbed on the surface and they undergo chemical reaction. There are some other reports in the literature, which including molecular dynamics simulations, which show that indeed this is an important reaction for catalytic carbon-based tribofilm formation. So carbon-hydrogen bonds are broken first, and then carbon-carbon bonds are broken. And then these fragments or species recombine on the surface and form a carbon-based tribofilm. In high entropy alloys, in our case, nickel, cobalt, chrome, a medium entropy alloy, the presence of multiple principal elements in the lattice provides enhanced catalytic activity. And I'm illustrating this through the schematic here In pure metals, you have elements of same size occupying lattice sites. The lattice is very happy. There is less distortion in the lattice. Similarly, in dilute alloys, there are few solute atoms, and that causes some distortion, but not a lot. But in multi-principal component alloys, the presence of multiple elements in lattice sites causes a lot of distortion. And that lattice distortion is believed to promote catalytic activity because that causes the potential energy of the alloy to be high, and that reduces the effective energy barrier for chemical reactions. So we think that this is a very important mechanism that provides enhanced catalytic activity in these high entropy alloy catalysts. And so we can exploit their catalytic activity to design mechanical systems, mechanical components, coatings, and that can provide excellent wear resistance by generating lubricious tribofilms from ambient air. Now, this result is also very remarkable because most prior studies on catalytic materials require a lubricated contact to generate tribofilm. It could be an oil molecule like the study shown on top here, where polyalpha olefin is supplied to generate carbon-based tribofilm. Or it could be vapor phase lubricant, where the organic vapors are introduced in the chamber and those molecules react and form tribofilm. Unlike these prior studies, in our system, we can generate these tribofilms in air, in ambient conditions, which is remarkable. So now I would like to switch gears and talk about mechanochemical reactions under electric fields. So this is a very important topic in recent years because of growing interest in growing adoption of electric vehicles for sustainability and for reduced carbon dioxide emissions. However, when drivetrains are electrified, there can be stray currents, and a combination of stray currents and mechanical stresses can sometimes be a recipe for disaster. And there are multiple reports which show that the lifetime of components or the failure rates are enhanced in the presence of electrical currents. There are also some studies which show that the presence of electric fields can affect mechanochemical reactions at sliding contacts. So here I'm showing a literature on zinc dialkyl diethiophosphate tribofilm, and under no electric field condition, this additive is known to form a tribofilm, and then that tribofilm prevents wear of surfaces. However, in this study, when an electric field was applied, so 1.5 amps current was passed through the contact, the formation of tribofilm was suppressed, and instead the authors reported wear of surfaces. So clearly, electric fields affected the mechanochemistry of ZDDP tribofilm, and that affected the resulting wear properties. There are studies on ionic liquid tribofilms as well, where initially the application of some electric field has been shown to promote tribofilm formation. But when electric fields are further increased, the tribochemical reactions are suppressed, and instead, significant wear of surfaces is observed. And there are multiple other studies. These are just a couple of studies I picked from the literature. Multiple studies show electric fields affect tribofilm formation and their frictional and wear properties. However, the fundamental mechanisms by which electric field affect reactivity still remain not very well understood. And moreover, it is extremely challenging to model mechanochemical reactions in the presence of electric field. So we need to develop a better understanding of the mechanisms of these reactions. So to do that, we used an in-situ tribometer, so we can study chemical reactions, the mechanochemical reactions as they are happening. So this is a electrified mini traction machine from PCS Instruments, who are the sponsors of today's event. So an MTM consists of a rotating ball and disc specimens. They can be independently controlled, so we can study chemical reactions over a wide range of slide roll ratios. This system is also equipped with a spacer layer imaging system, which can be used to monitor the formation of tribofilms during the experiment. So here I'm showing you a video of tribofilm formation on a ball specimen. And then that allows us to do quantitative kinetic modeling or measurement of tribofilm growth at these interfaces. So unlike traditional MTM, we used an electrified MTM in our experiments. So essentially, we pass electric current through the ball disk interface. As you can see, it's an electrified MTM. We can pass currents through the interface, and that allows us to study the formation of tribofilms and the growth kinetics of tribofilms in the presence of electric fields, which we hope will help us develop fundamental insights into these tribofilm formation mechanisms. So for this study, we investigated a phosphonium phosphate ionic liquid. This is an oil-soluble ionic liquid, which has been extensively studied. It is known to provide excellent wear resistance by forming a tribofilm in several experiments, several prior studies by Dr. Junkyu's group at Oak Ridge National Lab. And it has been shown that these additives form a tribofilm composed of iron phosphate and iron oxide. And these tribofilms then protect the surfaces from wear. So we tested and of course, all these prior studies are done on, most of these prior studies are done on under unelectrified conditions, so traditional mechanochemical conditions. So in this study, we investigated the formation of tribofilms by this ionic liquid in the presence of electric field using MTM. And we obtained these samples from Dr. Junkyu's group at Oak Ridge National Lab. So we added 1% phosphonium phosphate in PaO2 oil, and then we conducted the tests under the conditions I have listed here. So initially at 0 amp, without any current applied, we barely saw any tribofilm growth under these test conditions. It was very thin film and hard to quantify using SLIM. However, when we applied 25 milliamp current, we clearly saw an acceleration in the growth of the tribofilm, right? We can see a thicker film formed much more rapidly, and then it sort of saturated towards the end of the 2-hour-long experiment. And then we further increased the applied current to 50 milliamp, and that produced even thicker film. And we saw this behavior until 125 milliamp, where the application of current enhanced film growth kinetics and produced thicker tribofilms. However, when we further increased currents to 150 milliamp, 200 milliamp, the growth kinetics was actually suppressed. So we did not see further benefits of applying electric field through the ball disk interface. We can zoom into this early 5 minutes of the experiment, which is where most of the film growth takes place. And again, I can show you very clearly here, the growth kinetics of the tribofilm increases initially up to 125 milliamp, but then further increase in current actually resulted in thinner films. So that effect of that enhanced tribochemistry was suppressed after a critical current value. So we can extract the growth rate of these tribofilms by just doing a linear fit. So we just assumed that the growth kinetics of these tribofilms followed zero-order kinetics. And so we can do a linear fit and obtain rate constant as a function of applied current. And we saw that up to 125 milliamp, there was an exponential increase in rate constant with applied current. But then with further increase in current, actually, the growth was suppressed, and we did not see that exponential increase anymore, which we think happens because of wear activated at these higher currents. And I'm going to show those results in a moment. So once again, I will go back to this important potential energy surface schematic I showed before. And we have discussed this already, how mechanical energy plays an important role in mechanochemical reactions. They reduce the effective energy barrier for a chemical reaction to take place, and that's given by this Arrhenius-style equation. We propose to extend this framework to capture the effect of electric fields on mechanochemistry. So we propose that electric fields could further provide a reduction in energy barrier of mechanochemical reactions. And this can happen either by a change in reaction pathway or by providing more energy to the reactants. And so we introduce a new parameter in the Arrhenius style equation, EI, which captures the electrical energy supplied to the system. And we can further write this, decompose this EI parameter as a product of the applied current I and a new activation parameter delta phi. So we take this, inspiration, it's an analogous to the sigma delta V that captures the effect of stress. We extend that concept to capture the effect of applied current on mechanochemical reactions. And so we can apply this framework and obtain to our experimental results that I showed you in 2 slides ago. And we can get the value of this activation constant, delta phi. And so we propose that this theoretical framework can help us predict the reactivity of lubricant additives at electrified contacts. So higher the value of delta phi, more susceptible the lubricant additive would be to electric fields. So in other words, the higher the delta phi, the higher would be current-induced acceleration of mechanochemical reactions. And this will help us model the behavior of, model the kinetics of mechanochemical reactions under electric fields. So in the future, we envision we can capture the value of delta phi for a wide range of additives with different molecular structures. And these values will provide fundamental insights into the molecular mechanisms by which electric fields affect reactivity. We also looked at the tribofilm morphology by scanning electron microscopy. So under unelectrified conditions, 0 amp conditions, we saw typical striations that are seen on running tracks because of shear stresses at these sliding contacts. So very striated morphology. At 100 milliamp, we clearly see that there is some kind of deposit on the running track, which is consistent with our in-situ slim measurements. But at the same time, we also saw the formation of small pits on the tribofilms. So electric fields are promoting tribofilm formation, but they're also generating these small pits on the surfaces. So we investigated these pits as a function of applied current. So if we looked at multiple tribofilms that we generated across test conditions, and we observed that the pitting density increased exponentially with applied current. So our results suggest that the electric fields promote both tribofilm formation and micropitting. And these two mechanisms, we think they compete with each other, which I think is what leads to a suppressed tribofilm formation at very high currents. So initially, tribochemical reactions are more dominant, and that's why we see an exponential increase in the reaction rate constant. But beyond a critical current, the micropitting wear becomes much more dominant, and we stop, and that undermines the mechanochemical film formation at these interfaces. We also looked at the composition of these tribofilms, and they are composed of phosphorus and oxygen, which is consistent with previous studies on phosphonium phosphate ionic liquid films generated under unelectrified condition. The application of electric field did not change these elemental compositions significantly. We also looked at their composition by Raman spectroscopy. So this work was done with Professor Ken Kalkin's group at Oklahoma State. And we saw that the tribofilms were primarily composed of iron oxide and iron phosphate, along with some carbon peaks. So the composition of the tribofilms was more or less similar for both unelectrified and electrified condition. So the application of electric field did not change the chemistry of these tribofilms significantly. This outcome was further corroborated by X-ray photoelectron spectroscopy, which also suggests the films are a mixture of iron phosphate, iron oxide, and hydrocarbons. So based on these results, we conclude that the application of electric field generates more tribofilm, and that is because it accelerates mechanochemical reactions. In the case of phosphonium phosphate additives under these conditions, we think that the reaction outcome is same. So the final composition of the films are more or less comparable, but it's the amount of tribofilm or the yield of tribofilm that is increased when the electric fields are applied. So the difference is more in kinetics rather than the reaction pathway itself. So to conclude my talk, we discovered that multi-component nickel-cobalt-chrome alloy can catalyze carbon-based tribofilm formation from ambient hydrocarbons, so the hydrocarbons in air. The growth of these tribofilms follows the stress-assisted thermal activation model. So the film growth is promoted by both stresses and temperatures. We also studied the mechanochemistry of phosphonium phosphate ionic liquids under electric field, and we discovered that electric fields enhance tribofilm growth. And we propose a new kinetic model that captures the reactivity of additives under electric fields. We discovered that there is a competition between mechanochemical reactions and micropitting wear. And at very high currents, the micropitting wear dominates and undermines mechanochemical reactions. So as I said earlier, the results I showed you today were primarily an outcome of the PhD research of my students, Banti Tomar and Foyez Ahmad, along with contributions from the research groups of Professor Ritesh Sachan, Dr. Jun Kyu, Professor Kan Kalkan, and Professor Dave McElroy. With that, I thank you for your attention. We will have time to interact during the Q&A later, but also if you have any further questions or if you would like to interact more, this is my email address. Thank you very much.
Thank you very much, Pranjal. That was a fantastic talk. It's okay, I can turn the screen share off here. And now, everyone, we will be welcoming Alexander McLaren from PCS Instruments on stage in order to deliver the presentation from PCS. So we'll welcome Pranjal back for the Q&A, as he said. I have some additional poll questions I will be releasing, and then we will also be looking at the releasing the handouts as well throughout this talk. So brilliant. I can see the slides, Alexander. I'll leave stage. Please take it away.
Thank you so much, Sam, and thank you, Pranjal, for a fantastic talk. That was really interesting. I'm Alexander. I work at PCS Instruments, and I'm just going to talk a little bit about how we're contributing to research in mechanochemistry and beyond. Pranjal very eloquently spoke about the influence of electric potentials on triboelectrochemistry and mechanochemistry in the contact, but also, of course, the influence of contact pressure and the influence of the environment, the ambient environment, all of which are things you might want to control. Equally, shear stresses are very important, and the ability to measure tribofilm topography. And all of these techniques are things that we have implemented on our tribometers at PCS, and techniques that we have developed over the years. So, of course, our bread and butter is kind of friction and wear measurement, but we also have a rig that can go up to 7.1 gigapascal contact pressures. The new HFRR has the ability to control both temperature and humidity of the environment, as well as, of course, the test sample. And we have a high pressure reciprocating rig, the HPR, that can go up to 10 bar pressure if you so need. Mechanochemistry is also critical in rolling contact fatigue. And so we have a rig that can achieve 1 million contact cycles per hour if fatigue is your thing. And of course, Pranjal talked about the spacer layer imaging method, which is a way of capturing the topography of either a tribofilm or an EHL film. PCS Instruments are designers and manufacturers of tribology lab instruments, and we've been around for almost 40 years now. In 2 years' time, it'll be 40 years. Our main markets are fuels and lubricants, but we also work in lots of other different industries, like biomedical, to food science, to personal care. So if you have an interesting tribology problem, do get in touch. We're always excited to hear from you. If you want to know more, do keep up with our podcast, which is called Tribology Talks and available from wherever you get your podcasts from, or our client stories on the website. We also have insights, articles, and our newsletter, and do give us a follow on LinkedIn as well if you want to keep up to date. I find this really useful personally. We don't collect any data from this app. It's just a gift from us to you. It's like a little Hertz contact calculator. If you happen to use any of our rigs, it's particularly easy, but it can also achieve arbitrary contact conditions and material parameters. So on iOS or Android, do give our PCS Instruments app a download if you want Hertz contact calculations at your fingertips. Parker mentioned the space layer imaging method as a way of measuring tribofilm thickness, and he also mentioned the work of Robert Karpik. It so happens that I collaborated with Robert Karpik a couple of years ago on some new algorithms for the analysis of tribofilms using SLIM. And since I've joined PCS Instruments, I've now implemented those algorithms in a new software package, which is free for you to use if you're already a PCS Instruments customer. So if you're interested in more robust and more reliable SLIM measurements, do get in touch either with PCS or with me personally, and I will hook you up with this software package. It's really exciting. We are always excited to hear what our customers are working on and how we can best support you in the future. So please do get in touch, tell us what you're interested in. And if you could answer the poll questions, we'd really appreciate that. There are just 4 different questions which Sam is gradually releasing. You can also get in touch with us via the website. So give us a phone call, send us an email, or we have a little chatbot which automates the process of raising a support ticket or asking us a particular question, which will save you time. We've covered a small portion of what we do at PCS today relevant to mechanochemistry, but we also have everything from viscometers to scuffing testers and lots of things in between. So if you are interested, once again, please get in touch. Thank you for your time, and I hope I'll see you soon.
Thank you very much, Alexander. So a good quick whistle-stop tour through everything the PCS does.
Yeah, that's the pitch.
There we go. That's it. So as we said, all of the poll questions are now available in the polls tab. So please do go have a look at those if you haven't already. And as well, we have handouts for all of the main pieces of equipment and some extras that was discussed during the webinar today. Now it is time for the Q&A. But before we begin that, let me just release the attendance certificate. So that is now available down in the bottom left-hand corner. So you click on that, input your details and email address, and you'll be emailed your attendance certificate. So we've got quite a few questions, which is excellent. So I'm glad to see that everyone was nice and curious about the content of the presentation today. So we've got the first one from Sahel here, who says, "Hi Pranjal, excellent talk. Is there any fundamental relationship between formation of tribofilm and the melting point of the material?"
Okay, so I'm assuming that this question pertains to the first part of my talk on catalytic alloys. So we have not investigated it, and it will not matter under the test conditions that we are dealing with, because the chemical reactions are, so essentially the tribofilm is formed by the reaction of ambient hydrocarbons. And the catalytic surface, the material, nickel, cobalt, chrome, is catalyzing that chemical reaction. So its melting point does not play a dominant role under these test conditions. Now, if we were to conduct tests under very high temperatures, where the melting point plays an important role, not because of melting per se, but because the other mechanical properties are closely tied to the melting point of the metal. And so if the mechanical properties change as a function of temperature, that is going to change the mechanochemical environment under which the reaction is taking place. So it could play a role. But under moderate temperature conditions we are dealing with, no, they do not play a role.
Okay, thank you. Got a question here from Andreas, who asks, on slide 16, excuse me, there was an exponential increase in the tribofilm thickness in the first 5 minutes. Did the tribofilm retain the thickness or wear out with further sliding?
That's a great question. So the tribofilm thickness was reduced subsequently, and then they reached a saturation. So yeah, there is a rapid buildup of tribofilm, and then there is wear of tribofilm, and then finally they saturate at a lower thickness. That ultimate thickness is on the order of 5 to 8 nanometers, whereas that initial buildup can be as high as 20 to 25 nanometers. So there is some removal that happens over time. I should point out that, with SLIM, we are looking at what's happening on the ball surface, right? So everything you saw with respect to the in-situ tribofilm growth behavior, that was capturing film thickness on the ball. Sometimes, if there is a removal of tribofilm from the ball surface, it could very well be transferring to the disc surface. And this back and forth process can continue in tribology tests. So that removal of film is not necessarily because the tribofilm is just wears off, but it could be due to that transfer from ball to disc. And then ultimately it stabilizes. We did not investigate that, what's happening on the disc surface in this study.
That would be quite interesting to see, though. But yeah, thank you. Okay, another question here. This time from Yu Yang, who asks, "Thanks for the excellent keynote, Pranjal. A little bit confused about the concept of mechanochemistry and tribochemistry. Is there any clear difference between those two concepts?"
Well, that's a great question, and I'm glad you asked. So mechanochemistry, tribochemistry is a subset of mechanochemistry. So mechanochemistry broadly captures chemical reactions under a variety of stresses, compressive, shear, tension, everything, everything is captured in mechanochemistry. Tribochemistry is more specifically applied to tribological interfaces, so at sliding contacts, rolling contacts. And the fundamental difference is that, when we talk of tribochemistry, shear plays the most important role in those chemical reactions. And there are some studies which have actually looked at the effect of different stress components and shown that shear is extremely important for the tribofilm formation by lubricant additives. So that's the key difference. Tribochemistry is a subset of mechanochemistry, and it primarily focuses on shear-induced processes and does not take into account other types of mechanochemical reactions, like if you stretch a molecule or if you just compress the molecule without any shear.
Okay, thank you. Yeah, it's a very good point to make, because I think in tribology, for those of us who may come into it from a more physics or engineering point of view, you get people that go, "I'm very unfamiliar with the chemistry that goes on." So thank you. Got a question from Ray. I hope I'm pronouncing that correctly. They say, "Hi Pranjal, excellent talk. How could you be certain that it's micropitting and not pits caused by electrical arc damage? In addition, what was the voltage that was applied, please?"
Right. So again, good question. These pits very well could be due to electric arc. And I should clarify, when I use the word micropitting, maybe I should use the word micron-sized pitting. Please don't think that I was referring to widely reported micropitting mechanisms in tribology literature, which have their own specific mechanisms. Here I'm talking of pits that are microscopic pits, as you saw in the electron micrographs. But thanks for clarifying this. They could be due to electric arc damage, indeed. The voltage in our experiments were very low. They were less than 1 volt. And of course, they changed as tribofilm formed. They typically increased with time because of increase in contact resistance. But they were always less than 1 volt.
Okay, thank you very much. Ooh, here's a good question from Xi Zhuan. I, once again, hope I'm pronouncing that correctly. "Hi Pranjal, how does the applied electric field affect the friction coefficient in your experiments?"
Good question, and I expected this question, so I will share my screen here, and I hope you can see the result now. So The traction coefficient increases at higher applied currents. And that is because, there is a more tribofilm formation at the interface. And so the roughness of the interface changes, and all of that affects traction coefficient. So we do see a relationship between current and tribofilm formation. And we think that that relationship is primarily because of the extent of mechanochemical reaction that takes place. This is similar to what people have reported for ZDDP and other types of tribofilm formation. The growth of a tribofilm is often accompanied by an increase in traction coefficient, and that's what we are seeing in these tests. You can also see one more important feature here. As the tribofilm thins over time, the traction coefficient also goes down. It's trending down if you watch here from 10 minutes to 120 minutes. And that is consistent with the film thickness measurement that we reported using In-situ Slim. And I will just show that real quick also for a recap. The film thickness decreases, correspondingly the traction coefficient also decreases.
Excuse me. To that, one thing that we often see is because customers tend to use super finished specimens so that they have very, very repeatable tests. When you build a tribofilm, you roughen the surfaces in contact, and because the specimens are so smooth to start with, that roughening massively changes the way the contact works, and therefore friction changes very drastically. Of course, in a machine element, that wouldn't be true because you'd have some roughness to start with. And so the roughening effect would be less strong, and perhaps the effect on traction would be less strong. And that's just another caveat to put on that.
That's a very good point, yeah.
Okay, thank you both very much. I have a question here from Irfan. It says, hi Pranjal, under electrified conditions in tribological systems, which parameter is more critical, current or voltage? I noticed that many studies tend to focus on one while often neglecting the other. Could you clarify the relative importance of each parameter in such experiments? I'd love to hear your opinion on this.
Well, thank you for this question. And before I attempt answering this question, I will say that I probably cannot clarify this question very well. Here is the deal. So current and voltage are interrelated. So in my test, I systematically varied the current and the voltage also, as a result, when the tribofilm formed and any changes in the tribochemistry affected the voltage, right? So we were measuring voltage. You can reverse the situation and do a test where you control the voltage. And in that case, the applied current would need to increase if we are building up a tribofilm that increases contact resistance, like we saw in my experiments. So they are interrelated. And you are right, there are some studies in the literature which control current and some which control voltage. And there are some multiple reports which suggest what the expected values of currents and voltages are likely to be in drivetrains of electric vehicles. But, at the same time, that is going to be different for drivetrain of Tesla versus drivetrain of Ford. So there are the way the drivetrains are designed, things will change. So we selected our test parameters carefully so that we are within the range of currents that multiple previous studies have reported to be commonly seen in drivetrains. And I would like to actually extend this further. There is a good wealth of data on wind turbine tribology, and there's some mechanisms due to electric field and wear mechanisms due to electric field are also widely reported. And they have conducted tests in milliamp current range that my study reported. So that also motivated the selection of these conditions. Lastly, some of the reasons for selecting current over voltage were just practical. We did not want to damage the MTM system, which actually we did once by passing too much current through the wires. And so, doing a current control test helps us make sure we are not doing that again. And so that's a practical reason for using current instead of voltage. But I probably have not answered your question all the elements of your question, but these were some of the motivations for selecting the conditions.
I might briefly add to that as well. This is something that we also see customers widely misunderstand, because of course current and voltage are linked by the resistance of the whole system. And very often this system not only has the contact resistance in it, but in series with that there's often a balance resistor. And the job of the balance resistor is if the contact resistance drops to 0, it limits the current to a finite current, because of course the voltage source would attempt to pass as much current as it could to drop that voltage across the system. And so you then have this third variable, the value of the balance resistor, which changes the volt amp characteristic of the whole system as you vary the contact resistance. And so actually many people's triboelectric systems are neither voltage nor current controlled. They have a linear characteristic, and as the contact resistance changes, we move across that line on the volt amp graph. It's important to understand that, because obviously there is no ideal voltage source and there is no ideal current source that will pass a constant current. They all have limits, and those limits in a tribological system where resistance can vary from 0 to infinity very quickly and on very short time scales, those limits will be reached. And so we have to have a system where we set those limits in intelligent ways that give us thermodynamic drivers that are predictable and that we can understand their effect. So the narrative around voltage and current as this kind of 2-parameter system is limited and flawed in that way if you don't understand the nuance.
No, thank you both very much. There's very important points to clarify, because I think we've had a comment in chat there saying, "Oh, you didn't, you didn't control that parameter." But as we've just explored, it's a little more complicated than that. So I'm just aware of time, but we have one final question remaining. If you two both don't mind that we cover this question, and then we'll draw the event to a close.
Sounds good.
Okay, excellent. Another question from Sai, I think, who asked a question earlier. Hi, Pranjal. I had a question regarding tribofilms in natural environments. Are these always influenced by hydrocarbons present in the atmosphere? Also, I've come across the idea that tribofilms can form due to wear particles generated between contact surfaces. If that's the case, why is tribofilm formation often attributed primarily to chemical reactions rather than mechanical interactions?
So good questions. Indeed, anything that is in the system and that can adsorb on surfaces is bound to affect the mechanochemical reaction. So, if you're conducting an experiment in ambient conditions and there are molecules that have an affinity for test surfaces, steel in my case, or nickel cobalt chrome actually for the catalytic case, they are going to influence the reaction. So often multiple molecules can compete for surface sites, and that affects the subsequent mechanochemical reactions. Now, if the molecules do not have an affinity for the surface, then they don't matter. Also, if the system, for example, if you're doing a lubricated test, and there are very strong chemistries with very strong groups that adhere to the metal preferably, they're going to just dominate, and other molecules won't be playing a dominant role in mechanochemical reaction. So that's the influence of hydrocarbons in the atmosphere, right? It depends on the competition of molecules and what are the reactants that we are talking about. You raise a good point that where particles could be integrated in tribofilms. That is correct. They can be integrated in tribofilms. Multiple studies have shown tribofilms that are composed of the additives, the species that are formed by reaction of additives, along with wear debris. Now, the last part of your question says, if wear debris are included in the tribofilms, then why is it attributed primarily to chemical reactions rather than mechanical interactions? You make a very good point here. To be more accurate, yes, there is a combination of mechanical wear and chemical reactions. Both are activated, right? Because you have high shear stresses at the interfaces. They are going to start causing wear of surfaces, start generating wear debris. But then there are also reactive molecules and many lubricants and they are going to undergo chemical reaction and form a product. So both processes can happen simultaneously. And so you're correct in pointing out that it's not necessarily just chemical reaction that happens at the interface, and that the tribofilm that is formed is not strictly due to chemical reaction, but there could be the contribution of wear particle generation. We are very much cognizant of this issue, and so we controlled this carefully in our catalytic experiments. So we used AFM technique intentionally because it's a single asperity contact generated by a sliding AFM tip on the alloy surface. And unlike some other techniques where there are multiple asperities rubbing against each other and wear takes place and reactions take place simultaneously, we try to keep the system cleaner, and AFM helps us achieve that, right? Which was visible in the images that I showed. The other point I should also make, even in macro scale tests like MTM, you can minimize the contribution of wear by carefully selecting your lambda value. Without diving deep into the concept of EHL, I would just say that you can select the speeds such that the extent of asperity interactions is controlled, and that can help us attain a regime where chemical reactions are much more prominent than wear debris generation. So we did that careful analysis and selected the test conditions in the second part of my test, presentation on ionic liquid tribofilms. We tried to minimize the regime where the wear debris is generated and integrated in films, but we cannot completely rule it out. You're correct.
Okay, thank you very much. Yeah, it's very important points once again. So I think, unfortunately, we are slightly over time, but we've gotten through all of the questions. So thank you very much to the both of you for staying a little longer in order to do that. And it's now time to bring the event to a close. So with that, thank you very much, Pranjal, for your fantastic talk, and also to you, Alexander, for your excellent talk and showing us everything that PCS Instruments can do. I'm going to release. We're just going to swap over the featured action so you can see the registration link for our upcoming event at the end of this month, and just cover a few thank yous before we close out. So thank you very much to PCS Instruments for the support for this event. As I say pretty much at the end of all of these events, we wouldn't be able to do what we do without our partners. So it is fantastic to have them involved. As a reminder as well, please do visit our website where you can view more of our videos. The website will soon be updated with the new event. You can see our archive of previous webinars, as well as mini symposia and some of our workshops. On the website as well, you can find a link to our LinkedIn page, wherein you can see some of our regular posts offering useful content on the fields of material science, tribology, and engineering. Now that our newsletter is no longer releasing, the content from that is now being released as regular LinkedIn posts. And finally, to you, the audience, thank you very much for staying with us. And we'd just like to ask for your support to take the time to advertise these lectures to your contacts. It would be great to keep growing our audience and keep spreading the word about what we're doing. So with that, thank you all very much. See you next time. And I hope you have a great rest of your day.
Thank you.
Thank you so much.
Thanks, everyone. Bye.